Problem 1 covers learning outcomes 5B, 5C, 7A, and 7B. For Part A, the goal is to calculate the relevant convective heat transfer coefficient. Water is flowing through a cylindrical pipe in your water feature, which covers forced internal convection, 7A, and cylindrical coordinates, 5B. The velocity is given, as well as the pipe diameter, and inlet and exit temperatures. Through the information given, you need to calculate the convective heat transfer coefficient. Properties are found in Table A9 at a temperature of 25 degrees Celsius, the mean temperature. After finding the Reynolds number to be greater than 10,000, indicating turbulent flow, you use the appropriate Nolsa number equation and then solve for H, which was calculated to be 4.58 times 10 to the 3 watts per meter squared times Kelvin. In Part B, water is forced to flow over a spherical rock, so this problem covers learning outcomes 5C, spherical coordinates, and 7B, external forced convection. Properties are found at the film temperature, while mu infinity and mu surface are found at their respective temperatures. Using the appropriate Nolsa number equation for flow over a sphere, where the convective heat transfer coefficient can then be calculated. From there, the heat transfer rate can be found. Here, Q equals negative 16.6 kilowatts, so the heat transfer rate is away from the rock. Problem 2 covers learning outcomes 7C and 7D. In boiling water, you see that the change in excess temperature is 7 degrees Celsius, so this is a nucleate boiling problem covering learning outcome 7D. After finding the water properties at the saturation temperature from Table A9, you plug them into the nucleate boiling equation, and you get a nucleate boiling flux of 48.3 kilowatts per meter squared. In Part B, you see that you are allowing a horizontal hot plate with water properties to cool, so this is natural convection, which is learning outcome 7C. The film temperature is the temperature that you get the fluid properties. After finding the Rayleigh number, you use the correct Nolsa number equation and then can solve for the heat transfer rate after calculating the convective heat transfer coefficient. For this part, Q is equal to 367 watts. Problem 3 covers learning outcomes 6A and 6B. In seeing that your bike tires are deflated, you decide to model it as steady-state mass diffusion, learning outcome 6A, in Part A. This is through a cylindrical element. The inner and outer mass fractions are known, and you assume steady-state mass diffusion. Then you use the mass diffusion equation for a cylinder and find the density at the given temperature. The mass diffusion rate that you find is 5.72 times 10 to the negative 10 kilograms per second. In Part B, you assume transient mass diffusion in a semi-infinite medium, learning outcome 6B, and therefore use the error function equation to calculate the mass fraction after the specified time and with the specified thickness. The mass fraction of N2 that you find is 0.0913. Problem 4 covers learning outcome 8A. This problem covers this learning outcome by modeling a double pipe counterflow heat exchanger with a heart. The hot and cold specific heats can be looked up in Table A9 at the specified temperatures, assuming the fluid is similar properties to water. From there, the C constant can be calculated. Q max can be calculated with C min and the given inlet temperatures, so the effectiveness can be calculated. Then the NTU equation is used so that the overall convective heat transfer coefficient is found. Here, U equals 373 watts per meter squared times Kelvin. Problem 5 covers learning outcomes 8b and 9. This problem covers learning outcome 8b as a membrane is used to separate CO2 from N2, so this is a unit operations mass transfer. With the given information, the composition of the retentate stream is found, so that the partial pressures of CO2 in each stream can be calculated. The pressure of CO2 in the permeate is found by finding the flux of CO2, using the log mean partial pressure driving force. This problem also covers learning outcome 9 because solver is used to find the pressure of CO2 in the permeate, so numerical methods are used. Numerical methods can make this problem solvable due to the complexity of solving for a term in the log mean driving force equation. The pressure of CO2 in the permeate stream is calculated to be 12.5 kPa.